the universe, a vast space stretching tens of billions of light years in every direction. Yet, 13.8 billion years ago, it began as something unimaginably small, incredibly dense, and unbelievably hot. In one tiny moment, there was nothing, then suddenly everything, space, time, energy, and matter burst into existence in an event we call the Big Bang. But how did it all happen? What set this moment into motion? And why is it important for us, small beings on a blue planet, to understand something so massive and ancient? Understanding the universe's beginning isn't just about curiosity, it's about uncovering the connections that make up our reality. Every atom in your body, the carbon in your cells, the oxygen in your lungs, was created in the stars that formed after that first moment. To understand the universe's origin is to understand ourselves. Think of it like starting a story but skipping the first chapter. You might figure out some of what happens later, but the deeper meaning, the why behind it all, remains unclear. The universe is that story, and its first chapter holds the answers to its greatest mysteries. Was there truly a moment of creation? Or has the cosmos been expanding and contracting endlessly? Is ours just one universe among countless others? And what if we're living in a tiny part of something much bigger? What makes these questions even more exciting is how they connect science and philosophy. The birth of the universe challenges ideas about time, cause and effect, and existence itself. When scientists ask, what came before the Big Bang? They're also asking questions philosophers have debated for centuries. What does it mean for time to have a beginning? Is there a purpose to the universe, or is it simply the result of chance? Even the tools we use to explore these questions show the limits of human creativity. Giant telescopes look billions of years into the past, capturing faint traces of light from the first moments of time. Particle accelerators recreate the conditions of the early universe with incredible amounts of energy. And yet, for all our progress, we are still standing at the edge of a profound mystery, like standing on a shore and wondering what lies beyond the sea. As we begin this journey to understand how the universe began, we'll encounter groundbreaking ideas, puzzling questions, and concepts that challenge how we see the world. From the rapid inflation that shaped the cosmos to the strange particles that hint at other dimensions, the story of the universe's birth is not just about science. It's about us, our origins, and our place in the grand story of everything. So, let's dive in. Before any diving though, just one more thing. We know that the Big Bang created the universe, but here's your chance to create something even bigger, a slightly higher subscriber count on this channel. Don't miss out, be a part of history. Please give this video a like and subscribe to the channel. Thank you. Now let's begin. The story of how the universe began is as captivating as it is complex. Scientists and philosophers alike have proposed groundbreaking ideas to explain the birth of everything we know. Let's explore 5 major theories that attempt to unlock the mysteries of the universe's origin, starting with the interplay of space and time itself. Stephen Hawking, one of the most celebrated cosmologists, presented a perspective that reshaped our understanding of the universe's beginning. According to Hawking, space and time are not separate entities, but deeply connected, woven together like threads in a fabric. This idea forms the foundation of what we call space-time. Of course, as you probably know, the idea that space and time are interconnected into a single continuum known as space-time is rooted in Einstein's theory of general relativity. So, while Hawking didn't invent the concept of space-time itself, he certainly helped us understand its profound implications for the universe's beginning and structure. Hawking suggested that asking, what came before the Big Bang, might be as meaningless as asking, what's north of the North Pole? Just as the concept of north ceases to exist beyond the pole, time itself might have started with the Big Bang. Before that moment, there was no before, no time, no space. Just a singularity where all the laws of physics as we know them break down. To visualize this, imagine a balloon. As you blow air into it, the surface expands, representing the growth of space. Time, in this analogy, is inseparable from the surface of the balloon. There is no starting point or edge to the balloon's surface, just as there may not have been a before the Big Bang. This interconnected nature of space and time fundamentally changed how we think about the universe's origin. If the Big Bang was the spark that lit the universe, then inflation was the explosion that followed. Proposed in the 1980s by physicist Alan Guth, inflation theory describes a period of extremely rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During this time, the universe expanded exponentially, doubling in size over and over again at an astonishing rate. Why is inflation so important? For one, it helps explain some of the biggest puzzles in cosmology, such as the horizon and flatness problems. The horizon problem asks how regions of the universe that are far apart and have never interacted can have the same temperature. Inflation solves this by suggesting that these regions were once much closer together before the rapid expansion stretched them far apart. Similarly, the flatness problem, why the universe appears so geometrically flat, can be explained by inflation, which smoothed out any initial curvature in spacetime. To understand inflation, think of it like baking a loaf of bread. Tiny air bubbles in the dough represent quantum fluctuations in the early universe. As the dough rises, these bubbles expand. Similarly, inflation stretched the small irregularities in the early universe, magnifying them into the seeds of galaxies, stars, and planets. Without inflation, the universe would look very different from the structured cosmos we see today. What if our universe isn't the only one? This is the central idea behind the multiverse theory, a concept that takes inflation to its logical extreme. As the inflation theory evolved, scientists like Andre Linde expanded it into the idea of eternal inflation. According to this idea, inflation didn't just happen once. Instead, it continues eternally in other regions of a vast multiverse. Picture this. Our universe is like a bubble floating in a cosmic foam. Surrounding it are countless other bubbles, each representing its own universe with its own set of physical laws and constants. Some bubbles might contain universes with entirely different properties, perhaps ones where gravity is stronger or where atoms don't form as they do in ours. Most of these universes would be inhospitable to life, but a few might be similar to ours. The multiverse theory not only expands our understanding of the cosmos, but also offers potential answers to some perplexing questions. For example, why do the physical constants in our universe appear so perfectly fine-tuned for life? If there are countless universes, it's simply a matter of probability that one of them, ours, would have the right conditions for life to emerge. While this theory is difficult, or maybe impossible, to test experimentally, it provides a fascinating framework for thinking about the broader reality beyond our observable universe. While inflation suggests a beginning for our universe, the Big Bounce offers a different perspective, one of cycles. But where does this fascinating idea originate? The Big Bounce theory has its roots in attempts to reconcile the Big Bang model with quantum mechanics and general relativity. As scientists delved deeper into the nature of the universe's earliest moments, they encountered the singularity problem, the idea that the Big Bang implies an infinitely dense point where the known laws of physics break down. To address this, theoretical physicists explored alternative models that could bypass the singularity. One such model is the Big Bounce, which emerged from advancements in quantum cosmology and theories like loop quantum gravity, pioneered by figures such as Martin Boyerwald. According to this theory, our universe is just the latest in an infinite series of expansions and contractions. Instead of a singular Big Bang, the cosmos undergoes periodic bounces in which it expands, contracts, and then expands again. Imagine a bouncing ball. Each time it hits the ground, it compresses before springing back into the air. Similarly, the Big Bounce suggests that the universe compresses into a dense state before rebounding into a new phase of expansion. This cyclical model eliminates the need for a singular beginning, proposing instead that the universe has always existed in some form. One of the intriguing implications of the Big Bounce is that traces of previous cycles might be embedded in the universe we see today. For instance, certain patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, could hold clues about what came before. While still speculative, the Big Bounce challenges us to rethink the idea of a singular origin and consider a universe with no true beginning or end, which idea is possibly even more terrifying. Finally, we come to string theory, a bold and complex framework that seeks to explain the very fabric of reality. At its core, string theory proposes that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. These strings vibrate at different frequencies, giving rise to the particles and forces we observe. The idea is that what we perceive as particles, such as electrons and quarks, are actually different vibrational states of these underlying strings. String theory, however, is not only concerned with the nature of particles, but also introduces a mind-bending idea: the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. In this framework, our universe is a brane, a 3-dimensional slice of a much larger, multi-dimensional reality. Other branes could exist parallel to ours, separated by tiny distances in higher dimensions. This suggests a vast and complex cosmic structure beyond the boundaries of our immediate perception. The origins of string theory can be traced back to the late 1960s. Initially, physicists were attempting to understand the strong nuclear force, the force responsible for holding atomic nuclei together. Gabriele Veneziano and others discovered that a mathematical function known as the Veneziano amplitude could describe the behavior of strongly interacting particles. This was a breakthrough that led to the development of string theory. Initially, it was thought to be a theory purely for describing hadrons, particles like protons and neutrons, but by the 1970s, it became clear that the theory had much broader implications. Key physicists such as Leonard Susskind, Holger Beck-Nielsen, and Yoichiro Nambu showed that the theory could explain not only the strong force, but also all of the fundamental forces of nature: gravity, electromagnetism, and the weak and strong nuclear forces, by describing them as different manifestations of vibrating strings. One of the most fascinating aspects of string theory is the concept of brane collisions. According to some versions of string theory, the origin of our universe could have been the result of a collision between 2 such branes. Imagine 2 sheets of paper floating in the air, each representing a separate universe. If these sheets were to collide, the energy released could spark the creation of a new universe, potentially explaining the Big Bang. This idea not only provides a potential explanation for the beginning of our universe, but also hints at the possibility of other universes forming through similar collisions. The Big Bang itself could thus be the aftermath of such a brane collision. String theory's beauty lies in its ability to unify the forces of nature and offer a deeper understanding of the cosmos. By introducing a framework where gravity and quantum mechanics coexist, it provides a potential theory of everything that could unify the laws governing the smallest particles with the laws governing the largest cosmic structures. However, its mathematical complexity and lack of experimental evidence mean it remains a work in progress. Despite its elegance, string theory faces significant criticism, particularly regarding its falsifiability. Because the extra dimensions it predicts are so small and beyond the reach of current experiments, string theory's predictions cannot be directly tested with existing technology. This makes it difficult to verify through traditional scientific methods. Additionally, string theory's reliance on abstract mathematics without empirical evidence has led some to question its scientific status. Similarly, the multiverse theory, with its idea of an infinite number of universes, suffers from the same problem. The existence of other universes is inherently unobservable and unfalsifiable, making it a challenge for these ideas to be accepted as rigorous scientific theories. Still, the notion that our universe might be part of a larger multi-dimensional reality is as awe-inspiring as it is humbling. While string theory and the multiverse theory offer profound insights into the potential structure of reality, they remain speculative, awaiting a breakthrough that might bring them into the realm of testable science. Theories like these demonstrate the incredible ingenuity of human thought. Each one provides a unique lens through which to view the universe's beginning, offering insights into the nature of space, time, and existence itself. As we ponder these diverse ideas, from Hawking's view of space-time as an inseparable continuum to the far-reaching possibilities of the multiverse, we are confronted with a central question. What is the true origin of the universe? While these theories remain speculative, they push the boundaries of human knowledge and challenge our understanding of the cosmos. Some of them may eventually stand the test of time, while others may fall by the wayside. But each one, in its own way, brings us closer to unlocking the mysteries of the universe's birth. Yet, perhaps the most profound realization of all is that the universe's origin isn't just a scientific puzzle to be solved. It is a journey that connects us to the deepest questions about existence itself. Our search for answers is a reflection of our own curiosity, our desire to understand our place in the vastness of time and space. As we continue our exploration of the cosmos, these theories will guide us, but the ultimate answer may remain just beyond our grasp. Nevertheless, the pursuit itself, this quest to understand the unfathomable, is one of humanity's most remarkable endeavors. And so, with this foundation in mind, we now embark on the next chapter of our journey, the first step of the actual birth of the universe. From the first moments of inflation to the formation of the first atoms, we'll trace the steps that shaped the universe into the vast and wondrous place we now call home. The Planck era represents the earliest moment in the history of the universe, a time so brief, so extreme, and so mysterious that it challenges the very limits of our understanding. It's a fraction of a second after the Big Bang, lasting from 0 to 10 to the negative 43rd seconds, where the laws of physics as we know them break down. This is the stage where the story of our universe truly begins. To understand the Planck era, we need to think about almost unimaginable scales. Named after physicist Max Planck, this period is characterized by Planck units, incredibly small and fundamental measurements of time, length, energy, and temperature. For example, the Planck time, 10 to the negative 44 seconds, marks the smallest meaningful unit of time, and the Planck length, 1.6 times 10 to the negative 30 meters, is the shortest possible distance. During this era, the entire observable universe was compressed into a space smaller than a proton, with temperatures reaching 10 to the power of 32 Kelvin. In these conditions, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, indistinguishable force. Time, space, and matter, as we know them, didn't exist in the way we understand. Instead, the universe was a chaotic, seething plasma of energy and quantum fluctuations, a kind of cosmic cauldron where the familiar concepts of before and after didn't yet apply. To put it in perspective, imagine trying to measure the grains of sand on a beach, but your measuring tools dissolve every time you pick up a single grain. The Planck era is where our tools, our theories of physics, fail to provide clear answers, leaving us with profound questions about the nature of reality. One of the defining features of the Planck era is gravity's dominance. In our everyday lives, gravity feels like a relatively weak force. It can be overcome with a simple jump. However, during the Planck era, gravity's role was vastly different. At these tiny scales, it was as strong as the other fundamental forces, and its influence was deeply intertwined with the very fabric of space-time. This creates a monumental challenge for physicists. Our best theory of gravity, Einstein's general relativity, describes how massive objects warp space-time on large scales, like stars, planets, and galaxies. On the other hand, quantum mechanics, the science of the very small, governs the behavior of particles like electrons and photons. These two frameworks have been incredibly successful in their respective domains, but they are fundamentally incompatible with one another. General relativity breaks down when applied to the minuscule scales and extreme energies of the Planck era, while quantum mechanics doesn't account for gravity at all. This disconnect leaves scientists searching for a theory of quantum gravity, a single, unified framework that can describe how gravity operates on quantum scales. Solving this puzzle would not only illuminate the workings of the Planck era, but could also unlock new insights into black holes, the Big Bang, and the ultimate nature of space-time. To appreciate the difficulty, imagine trying to combine a symphony and a rock concert into a single, harmonious performance. Each has its own rules, its own rhythm and its own sound, but finding a way to make them work together is like trying to merge quantum mechanics and general relativity. Yet the Planck era demands we solve this riddle if we want to understand the universe's very first moments. In the 1950s, physicist John Archibald Wheeler introduced a striking image of what space-time might look like at the smallest scales during the Planck era. He called it quantum foam, a seething, turbulent froth where space-time itself becomes unstable and unpredictable. According to Wheeler, the familiar smoothness of space-time that we experience in everyday life dissolves at the Planck scale. Instead, space-time becomes a chaotic network of constantly appearing and disappearing tiny structures. Picture the surface of a boiling pot of water with bubbles forming, merging, and popping. But instead of water, this foam is made up of minute fluctuations in space-time itself. One fascinating implication of quantum foam is the possibility of microscopic black holes and wormholes spontaneously forming and vanishing. These tiny phenomena could create brief connections between different regions of space-time or even alternate dimensions. Although these effects are far too small to detect directly, they hint at the profound complexity and dynamism of the universe's earliest moments. Quantum foam also illustrates the limits of our understanding. Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, prevents us from precisely measuring the properties of space-time at this scale. Length, time, and energy all fluctuate unpredictably, making it nearly impossible to pin down the nature of reality in the Planck era. Yet, this very unpredictability may hold the key to understanding the quantum origins of the cosmos. To bridge the gap between general relativity and quantum mechanics, physicists have proposed several bold and ambitious theories. Each offers a unique approach to understanding the interplay of gravity and quantum physics during the Planck era. One idea is that gravity, like the other fundamental forces, has a particle associated with it. This hypothetical particle is called the graviton. The theory of the graviton originated from the development of quantum field theory in the 1930s, where the idea of force-mediated particles, like photons for electromagnetism, was applied to gravity. In the 1950s and 1960s, physicists predicted the existence of the graviton, a massless, spin-2 particle. If gravitons exist, they would mediate the force of gravity in the same way that photons mediate electromagnetic forces. Detecting gravitons, if they are indeed real, could provide the missing link between quantum mechanics and general relativity. However, their incredibly weak interactions make them extraordinarily difficult to observe, even with the most advanced technology. Another intriguing approach to understanding the quantum nature of gravity is loop quantum gravity, or LQG, which reimagines space-time itself as a kind of woven fabric. Unlike the smooth and continuous view of space-time in general relativity, LQG proposes that space-time is made up of tiny, discrete loops, similar to the threads that form a piece of cloth. These loops are considered to be the fundamental building blocks of space-time, and their interactions are thought to be key to explaining how gravity operates on quantum scales. The origins of loop quantum gravity date back to the 1980s, when physicists like Abhay Mehta, Carlo Rovelli, and Lee Smolin began to explore the possibility that space-time could have a discrete structure at the smallest scales. This idea grew out of the challenges in trying to merge quantum mechanics with Einstein's general theory of relativity. In contrast to string theory, which suggests that the fundamental objects are one-dimensional strings, LQG focuses directly on the geometry of space-time itself, proposing that its fabric consists of loops that represent quantum states of the gravitational field. These loops are organized into structures known as spin networks. What makes loop quantum gravity especially compelling is its ability to predict a pixelated or granular structure of spacetime, similar to the concept of quantum foam. This foam-like nature of spacetime suggests that, at extremely small scales, on the order of the Planck length, spacetime is not continuous, but rather consists of discrete quantized units. If this theory is correct, it could offer a method for studying the Planck era, the earliest moments of the universe, indirectly. Researchers may look for evidence of spacetime's discrete nature in the behavior of particles and waves, particularly in high-energy experiments that probe the smallest scales of space and time. Perhaps the most well-known attempt at a theory of quantum gravity is the already mentioned string theory. This framework proposes that all particles, including gravitons, are not point-like objects, but rather tiny vibrating strings of energy. The different vibrations of these strings give rise to the various particles and forces in the universe. String theory also introduces the concept of extra dimensions beyond the four we experience. These hidden dimensions could help unify gravity with the other fundamental forces. In some versions of string theory, the Planck era is explained as a time when these extra dimensions were compactified, folded up so tightly that they became undetectable in the present-day universe. The Planck era remains one of the greatest frontiers in cosmology. It's a time when our current understanding of physics reaches its limits, leaving us with tantalizing mysteries and groundbreaking theories. From the turbulent chaos of Wheeler's quantum foam to the elegant possibilities of loop quantum gravity and string theory, the quest to understand this era is a testament to human curiosity and imagination. By unraveling the secrets of the Planck era, we may one day unlock the ultimate story of how the universe came to be. The Planck era left us with a chaotic and mysterious cosmos, but it also set the stage for one of the most extraordinary transformations in the universe's history: inflation. This rapid, exponential expansion of space not only shaped the universe we see today, but also resolved some of the most perplexing problems in cosmology. Let's delve into how Alan Gough's groundbreaking theory of inflation revolutionized our understanding of the cosmos, how it laid the groundwork for structure formation, and how it eventually transitioned into the more gradual expansion we observe today. In the early 1980s, physicist Alan Guth introduced the idea of cosmic inflation, a period of exponential expansion that occurred mere moments after the Big Bang. During this brief but dramatic phase, the universe grew from an unimaginably small size to something much larger, doubling in size approximately 90 times in less than a trillionth of a second. To put this into perspective, it's like stretching a marble to the size of the observable universe in the blink of an eye. Why was inflation necessary? Gough's theory addressed two major puzzles in cosmology: the horizon problem and the flatness problem. The horizon problem stems from the fact that distant regions of the universe appear to have the same temperature, even though they are too far apart to have ever exchanged energy or information. For instance, light from opposite sides of the observable universe hasn't had enough time to travel between those regions since the Big Bang. So how could these regions have achieved such uniformity? Inflation solves this by proposing that the entire observable universe was once a tiny, connected region. Before inflation, these regions had plenty of time to interact and equalize their temperatures. Then, inflation rapidly expanded this tiny uniform patch into the vast cosmos we see today, preserving its uniformity on a much larger scale. The flatness problem relates to the geometry of the universe. Observations show that the universe is extremely close to being flat, meaning its overall curvature is negligible. However, for this to be the case, the initial conditions of the universe would have had to be fine-tuned to an almost impossible degree. Inflation provides a natural explanation. As space expands exponentially, any initial curvature becomes less noticeable, just as the surface of a balloon appears flatter as it inflates. In this way, inflation stretched the universe to such an extent that its geometry now appears flat, even if it started with slight curvature. Gough's theory also introduced the concept of a hypothetical field called the inflaton, which drove the rapid expansion. The inflaton field's energy created a repulsive force, counteracting gravity and pushing space outward at an accelerating rate. Although the exact nature of the inflaton remains unknown, its effects are written across the cosmos, offering a compelling explanation for how the universe transformed from the Planck era's chaos into the vast, structured expanse we see today. While inflation smoothed out the universe on large scales, it also amplified tiny quantum fluctuations that existed during the Planck era. These fluctuations, minute variations in energy density, became the seeds for the universe's large-scale structures, such as galaxies, galaxy clusters, and superclusters. To understand this process, imagine a calm pond with ripples spreading across its surface. Before inflation, the quantum fluctuations were like those ripples, tiny and seemingly insignificant. But as the universe expanded exponentially, these ripples were stretched into vast waves, with some regions of space becoming slightly denser than others. Gravity played a crucial role in amplifying these differences. The denser regions exerted a stronger gravitational pull, attracting more matter and growing even denser over time. This snowball effect eventually led to the formation of the first stars, galaxies, and clusters. Without inflation to stretch these quantum ripples into macroscopic variations, the universe might have remained a homogeneous, featureless expanse. The evidence for these early fluctuations can be seen in the cosmic microwave background, also known as CMB radiation, a faint glow left over from the Big Bang. The CMB contains tiny temperature variations, reflecting the density differences imprinted by inflation. These subtle patterns have been meticulously studied by telescopes like Planck and WMAP, providing some of the strongest evidence for the inflationary model. In this way, inflation didn't just expand the universe, it also set the stage for the intricate cosmic web of matter and energy that we observe today. From the smallest quantum scales to the largest galactic clusters, the fingerprints of inflation are etched into the very fabric of the cosmos. Inflation wasn't a permanent state. It is thought to have lasted for an incredibly short period of time, around 10 to the power of negative 36 to 10 to the power of negative 32 seconds. After this brief but transformative period, it came to an end, giving way to the slower, more linear expansion of space that continues to this day. This transition, known as reheating, marked a critical turning point in the universe's history. During reheating, the inflaton field's energy was converted into a hot, dense soup of particles. This process flooded the universe with radiation and matter, setting the stage for the formation of atoms, stars, and galaxies. Temperatures were incredibly high, but as the universe expanded, it began to cool, allowing particles to combine and form the first building blocks of matter. One of the key questions in cosmology is why inflation stopped. While the exact mechanism remains uncertain, some theories suggest that the inflaton field decayed into other particles, dissipating its energy and ending the period of rapid expansion. This decay also introduced tiny variations in the energy density, further contributing to the formation of large-scale structures. To visualize this transition, think of a balloon being inflated rapidly by a powerful pump. Suddenly, the pump stops, and the balloon continues to expand more slowly as the air inside stabilizes. Similarly, after inflation ended, the universe continued to expand at a much slower rate, allowing the forces of nature to take over and shape the cosmos into its current form. The end of inflation also marked the beginning of a new phase in the universe's evolution. As the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, began to operate independently, they governed the interactions of particles, leading to the complex structures we see today. The transition from inflation to linear expansion was not just a change in pace, it was the birth of the universe as we know it. Inflation theory remains one of the most transformative ideas in modern cosmology. By explaining how the universe expanded so rapidly and why it appears so uniform yet structured, it has reshaped our understanding of the cosmos's earliest moments. From the rapid doubling of space to the stretching of quantum ripples into galactic seeds, inflation set the stage for everything that followed. And while questions about the exact mechanisms of inflation remain, its legacy is clear. It was the moment when the universe truly took shape, transforming chaos into the cosmos. The formation of the universe's fundamental forces and particles was a pivotal moment in cosmic history. This was when the chaotic energy of the early universe began to transform into something more structured, setting the stage for the emergence of matter as we know it. In this chapter, we'll explore how the universe's forces split apart, how the Higgs field gave particles their mass, and how the first building blocks of matter came into existence. As we've seen, at the very beginning, all the fundamental forces of nature were unified into a single, indistinguishable force. During the extreme conditions of the early universe, this force governed everything, with no distinction between gravity, electromagnetism, and the strong and weak nuclear forces. However, as the universe expanded and cooled, this elegant unification began to break down. The separation of forces happened in stages, a process known as symmetry breaking. The first force to split off was gravity, the weakest of the four forces but the one that shapes the large-scale structure of the universe. As the universe continued to cool, the strong nuclear force emerged, followed by the weak nuclear force and electromagnetism, which were initially united as the electro-weak force. Imagine a frozen lake gradually thawing under the warmth of the sun. At first, the ice is a uniform sheet, but as it melts, cracks form, and the ice separates into distinct pieces. Similarly, as the universe cooled, the unified force melted, splitting into the distinct forces that govern the universe today. Each of these forces plays a crucial role. Gravity binds massive objects like stars, planets, and galaxies. Electromagnetism governs the behavior of charged particles and light. The strong nuclear force holds atomic nuclei together. The weak nuclear force is responsible for radioactive decay and nuclear reactions in stars. This gradual separation of forces created the framework for the interactions that would shape the universe's evolution. One of the most profound transformations in the early universe was the emergence of the Higgs field. This invisible field permeates all of space, and its discovery provided the answer to a critical question: why do particles have mass? Before the Higgs field came into existence, particles like quarks and electrons had no mass. They moved through the universe at the speed of light, unable to clump together and form the structures we see today. The Higgs field changed everything. As particles interacted with this field, they gained mass, much like how a swimmer moving through water experiences resistance. The key to this process is the Higgs boson, a particle associated with the Higgs field. Imagine a celebrity walking into a crowded room. As they move, people gather around them, slowing their progress. In this analogy, the celebrity represents a particle, the crowd represents the Higgs field, and the attention they receive is the particle's mass. The more interaction with the field, the more massive the particle becomes. The existence of the Higgs boson was confirmed in 2012 by experiments at the Large Hadron Collider, or LHC, at CERN. Physicists smashed protons together at incredibly high speeds, recreating conditions similar to those of the early universe. In the resulting data, they found evidence of the Higgs boson, a discovery that earned a Nobel Prize and cemented the standard model of particle physics. The Higgs field's role in imbuing particles with mass was critical for shaping the universe. Without it, particles would never have slowed down enough to form atoms, stars, planets, or life itself. The universe, as we know it, would be an empty expanse of energy. As the Higgs field did its work, the universe continued to cool and expand. You may feel like a lot of time has passed since the end of inflation. You couldn't be further from the truth. The processes we are talking about were extremely, unimaginably rapid. We are only about a billionth of a second after the Big Bang, when the first fundamental particles began to take shape. These included quarks, leptons, and gluons, the building blocks of matter. Quarks are the most basic components of matter. They come in 6 types, or flavors: up, down, charm, strange, top, and bottom. In the early universe, quarks didn't exist as isolated particles. Instead, they were part of a hot, dense quark-gluon plasma, a state of matter where quarks and gluons floated freely in a high-energy soup. Leptons, including electrons, also emerged during this time. Unlike quarks, leptons don't interact with a strong nuclear force, making them less affected by the quark-gluon plasma. Gluons, on the other hand, are the force carriers of the strong nuclear force. They act like glue, binding quarks together to form larger particles such as protons and neutrons. Imagine the early universe as a boiling pot of soup, with ingredients swirling chaotically. The quark-gluon plasma was this cosmic broth, teeming with energy and activity. As the universe cooled further, the quarks began to combine, forming the first composite particles. Up and down, quarks joined to create protons and neutrons, while electrons remained separate, waiting for the right conditions to form atoms. This period of particle formation marked a crucial step in the universe's evolution. Without it, there would be no atoms, no chemistry, and no life. The quark-gluon plasma, though short-lived, was the birthplace of everything we see in the cosmos today. The formation of fundamental forces and particles was a transformative chapter in the universe's story. From the elegant symmetry of unified forces to the emergence of the Higgs field and the chaotic quark-gluon plasma, these events laid the groundwork for all the complexity and beauty that followed. Understanding these moments brings us closer to answering the ultimate question: how did everything begin? The story of the universe's beginning is also the story of a cosmic imbalance, an asymmetry that allowed the existence of everything we see today. In the earliest moments of the cosmos, matter and antimatter were created in equal amounts. Yet, for reasons that remain one of the greatest mysteries in physics, matter came to dominate, while antimatter all but vanished. This chapter explores how this imbalance arose through symmetry breaking and the potential role of elusive particles like neutrinos in tipping the cosmic scales. In the moments immediately following the Big Bang, the universe was a sea of particles and antiparticles. For every particle, such as an electron or a quark, there existed a corresponding antiparticle with the same mass but opposite charge, a positron for the electron or an antiquark for the quark. When matter and antimatter meet, they annihilate each other in a burst of energy, leaving behind photons and other particles. In theory, this process should have resulted in a universe filled only with light and radiation, with no leftover matter to form stars, planets, or life. Yet, here we are, living in a universe dominated by matter. How did this happen? The answer lies in a phenomenon known as symmetry breaking. While matter and antimatter were created in equal amounts, tiny differences in their behavior allowed matter to edge out antimatter by the slimmest of margins. How tiny were these differences? Scientists estimate that for every 1 billion antimatter particles, there were about 1,000,000,001 matter particles in the early universe. So, very, very tiny. These differences, though small, were enough to leave behind a residue of matter that would eventually form the galaxies, stars, and planets we observe today. One possible source of this imbalance lies in the behavior of certain particles during the universe's earliest moments. For example, particles known as kaons, which are composed of quarks, exhibit a slight preference for decaying into matter rather than antimatter. This subtle difference in decay rates, called CP violation, short for charge parity violation, was first observed in laboratory experiments in the 1960s. CP violation demonstrates that the laws of physics are not perfectly symmetrical between matter and antimatter. Imagine a game of coin flips, where heads represent matter and tails represent antimatter. If the coin were perfectly fair, the number of heads and tails would be equal over time. But what if the coin was slightly biased, favouring heads by just a fraction of a percent? Over many flips, heads would begin to outnumber tails. In the same way, small asymmetries in particle interactions allowed matter to outnumber antimatter in the early universe. However, the observed level of CP violation in current experiments is not sufficient to explain the dominance of matter. This suggests that other processes or particles may have contributed to the asymmetry, leading physicists to search for new clues in the cosmic puzzle. One of the most promising candidates for explaining the antimatter imbalance is the neutrino. The neutrino is a ghostly particle that rarely interacts with anything. It can even pass through entire planets without being stopped. Neutrinos are incredibly light, nearly massless particles that were abundant in the early universe. While much is known about their behavior, scientists believe there may be a missing piece to the puzzle: the existence of right-handed neutrinos. In the standard model of particle physics, neutrinos are left-handed, meaning their spin aligns in a specific way relative to their direction of motion. Right-handed neutrinos, if they exist, would be their counterparts. Unlike their left-handed siblings, right-handed neutrinos would not interact via the weak nuclear force, making them even more elusive. However, their presence could play a critical role in breaking the symmetry between matter and antimatter. One theory suggests that right-handed neutrinos could decay in ways that favor matter over antimatter. During the earliest moments of the universe, when particles and antiparticles were being created and destroyed in rapid succession, the decays of these right-handed neutrinos might have introduced a small but crucial imbalance. This process, known as leptogenesis, could explain how the tiny preference for matter emerged and why the universe didn't end up as a featureless sea of radiation. The search for evidence of right-handed neutrinos is ongoing. Because they interact so weakly with other particles, detecting them directly is extremely challenging. However, experiments studying neutrino oscillations, the phenomenon where neutrinos change from one type to another as they travel, have provided tantalizing hints that neutrinos behave in ways not fully accounted for by the standard model. These hints suggest that neutrinos may hold the key to unlocking the mystery of the matter-antimatter asymmetry. The dominance of matter over antimatter is not just a question of particle physics. It is a story about the very existence of the universe as we know it. Without this imbalance, there would be no atoms, no chemistry, and no life. Every star that shines and every planet that orbits owes its existence to the tiny asymmetry that arose in the universe's earliest moments. Understanding this asymmetry is one of the greatest challenges in modern physics. Experiments at particle accelerators like the Large Hadron Collider, LHC, continue to probe the properties of particles and their antiparticles, searching for clues about how the imbalance arose. At the same time, astrophysical observations, such as studies of the cosmic microwave background radiation, provide insights into the conditions of the early universe. While much remains unknown, the progress made so far demonstrates the incredible ingenuity of human thought in this area too. From the discovery of CP violation to the study of neutrino oscillations, each breakthrough brings us closer to understanding the origins of the cosmic imbalance. The fact that we can even ask these questions, and in many cases, design experiments to test them, is a testament to the power of science. As we continue to unravel the mysteries of matter and antimatter, we are not just learning about the universe's past, we are also gaining insights into its future and the fundamental laws that govern its behavior. The imbalance that gave rise to everything we see today may hold the key to answering some of the deepest questions about existence itself. The story of matter and antimatter is a story of survival against the odds. From the perfect symmetry of the early universe to the tiny breaking of that symmetry, the journey from chaos to creation is one of the most profound tales in cosmology. As we explore the mysteries of neutrinos and CP violation, we are reminded of the delicate balance that underlies our very existence. The universe's triumph over annihilation is a testament to the power of even the smallest imperfections, a cosmic imbalance that made everything possible. Neutrinos are among the most enigmatic particles in the universe. These nearly massless particles, sometimes called ghost particles, barely interact with anything, making them incredibly difficult to detect. Yet they play a vital role in shaping our understanding of the cosmos. In this chapter, we'll explore the fascinating story of neutrinos, focusing on relic neutrinos from the early universe, their importance as a cosmic snapshot, and the immense challenges involved in detecting these elusive particles. To understand the role of neutrinos in the universe's history, we must go back to the first second after the Big Bang. As we have already discussed, during this time the universe was an incredibly hot and dense soup of particles. Among these particles were neutrinos, which decoupled from the rest of the matter, an energy approximately 1 second after the Big Bang. This decoupling occurred when the universe had cooled enough for neutrinos to stop interacting significantly with other particles. These relic neutrinos, often referred to as the cosmic neutrino background, or CNB, are a direct relic of the universe's earliest moments. Much like the cosmic microwave background radiation, or shortly CMB radiation, provides a snapshot of the universe approximately 380,000 years after the Big Bang. The CMB offers a glimpse into a much earlier period. However, unlike the CMB, which is relatively well studied, the CMB remains largely elusive due to the ghostly nature of neutrinos. Relic neutrinos are incredibly faint and have very low energies, making them exceptionally challenging to detect. They now move through the universe at speeds much slower than light, with their temperature cooled to just 1.95 Kelvin, only slightly above absolute zero. Despite their low energy and weak interactions, relic neutrinos hold the key to understanding the early universe. They carry information about the conditions that existed mere moments after the Big Bang, including the density, temperature, and dynamics of the primordial plasma. Imagine finding a fossil that predates all other fossils by billions of years. Relic neutrinos are that ancient record, a preserved trace of the universe's infancy. If we could detect and study them, they could provide unprecedented insights into the processes that shape the cosmos in its earliest moments. Detecting neutrinos is notoriously difficult due to their unique properties. They are electrically neutral, have extremely small masses, and interact with matter only through the weak nuclear force and gravity. As a result, trillions of neutrinos pass through your body every second without leaving a trace. To detect even a handful of them, scientists must have built incredibly sophisticated and sensitive detectors. The challenges of detecting relic neutrinos are even greater. These particles are much less energetic than the neutrinos produced by the Sun or supernovae, making them harder to distinguish from background noise. Despite these challenges, physicists have devised ingenious methods to study these particles, pushing the boundaries of technology and creativity. One of the most ambitious efforts to study neutrinos is the IceCube Neutrino Observatory, located deep within the Antarctic ice. IceCube consists of thousands of detectors embedded in a cubic kilometer of ice, designed to detect the faint flashes of light produced when high-energy neutrinos interact with the ice. While IceCube primarily detects neutrinos from cosmic sources like supernovae and gamma-ray bursts, its technology represents the cutting edge of neutrino research. Detecting relic neutrinos, however, will require even more advanced observatories. One promising concept is the use of ultra-cold detectors that could measure the minute energy changes caused by relic neutrinos interacting with specific materials. Another idea involves studying the imprints of relic neutrinos on large-scale structures in the universe, such as the distribution of galaxies. These indirect methods could provide clues about the properties and behavior of relic neutrinos, even if direct detection remains out of reach. To appreciate the difficulty of detecting these enigmatic particles, consider an analogy. Trying to catch a single grain of sand in a vast desert while blindfolded. Neutrinos pass through matter so effortlessly that even the densest materials, like lead, offer little resistance. A light-year-thick wall of lead would still fail to stop most neutrinos. This ghostly nature makes them both fascinating and frustrating for scientists. Despite their elusiveness, they are incredibly abundant, with an estimated 330 relic neutrinos per cubic centimeter of space. This abundance makes them a crucial component of the universe's overall energy density, influencing its expansion and evolution. By studying neutrinos, scientists can unlock new insights into fundamental physics and cosmology. Neutrinos are more than just cosmic curiosities. They hold the potential to answer some of the most profound questions in science. For example, studying them could help us understand why the universe contains more matter than antimatter, a mystery we explored in the previous chapter. Their behavior in the early universe might also reveal new physics beyond the standard model, shedding light on phenomena like dark matter and dark energy. Moreover, neutrinos serve as messengers from some of the most extreme environments in the universe. High-energy neutrinos detected by observatories like IceCube can provide information about cosmic events that are otherwise difficult to study, such as the cause of collapsing stars and the environments around black holes. Finally, relic neutrinos offer a unique opportunity to probe the conditions of the universe during its earliest moments. Once we'll have the technology to study these ancient particles, we may gain a deeper understanding of how the universe transitioned from its initial chaotic state to the structured cosmos we see today. The study of neutrinos is still in its infancy, but the progress made so far is nothing short of remarkable. From the discovery of neutrino oscillations to the detection of high-energy cosmic neutrinos, each breakthrough has opened new doors to understanding the universe. The hunt for relic neutrinos represents the next frontier in this exciting field, offering the potential to uncover secrets that have remained hidden for nearly 14 billion years. As scientists continue to develop new technologies and refine their theories, the role of these particles in the story of the universe becomes ever clearer. They may be difficult to study, but their importance cannot be overstated. They are the silent witnesses of the cosmos, carrying the echoes of its earliest moments and the keys to its deepest mysteries. In the grand tapestry of the universe's history, neutrinos are the threads that connect its past, present, and future. By unraveling their secrets, we come closer to understanding the true nature of reality and our place within it. Black holes, the fascinating objects that warp space-time and defy our understanding of physics, are often thought of as the remnants of massive stars. But there may be another, more mysterious category of black holes: primordial black holes. They may have formed in the earliest moments of the universe. These hypothetical ancient objects are not the products of collapsing stars, but rather the result of extreme density fluctuations in the infant cosmos. In this chapter, we'll delve into Stephen Hawking's theory of primordial black hole formation, explore their potential role as seeds for supermassive black holes, and consider how their existence might solve some of the biggest puzzles in galaxy evolution. Stephen Hawking, a visionary in the field of theoretical physics, proposed that black holes could form not only from the collapse of stars, but also from density fluctuations in the early universe. During the first second after the Big Bang, the universe was a turbulent and chaotic environment, with regions of slightly higher and lower density. These fluctuations, though tiny, were magnified by the rapid expansion of the universe during inflation. Hawking theorized that in areas where the density was especially high, the gravitational pull could become strong enough to collapse matter into black holes. These are what we call primordial black holes, or PBH for short. Unlike their stellar counterparts, primordial black holes could have formed at almost any size, from microscopic scales to masses equivalent to a large asteroid or even a small planet. Their formation depended on a delicate balance of conditions: the density of the region, the speed of the expansion, and the interactions between particles in the primordial plasma. One of the most fascinating aspects of primordial black holes is the incredibly short time window for their formation. The first second of the history of the universe was a period of rapid change, with temperatures and densities dropping dramatically as the universe expanded. If the conditions for PBH formation weren't met within this brief window, the opportunity would have been lost forever. This makes their existence a rare and fleeting phenomenon, tied directly to the unique conditions of the early universe. Although no direct evidence for primordial black holes has been found yet, their existence could explain several unresolved mysteries in astrophysics. For instance, PBHs might account for a portion of dark matter, the elusive substance that makes up about 27% of the total energy density of the universe, but has yet to be directly observed. If primordial black holes formed in large enough numbers, their combined mass could contribute significantly to the gravitational effects attributed to dark matter. Moreover, recent observations of gravitational waves, ripples in spacetime caused by massive objects colliding, have hinted at the possibility of merging black holes with masses that are difficult to explain through stellar evolution alone. These black holes could be primordial in origin, offering indirect evidence for their existence. Future gravitational wave observatories, like the Next Generation Laser Interferometer Space Antenna, or LISA for short, may provide further insights into the population and properties of PBHs. One of the most puzzling questions in modern astrophysics is how supermassive black holes, which can weigh millions or even billions of times the mass of the Sun, formed so quickly after the Big Bang. Observations have revealed the existence of these giants as early as 700 million years after the universe's birth, a time frame that challenges conventional models of black hole growth. Primordial black holes offer a compelling solution to this mystery. If PBHs formed during the early universe, they could have served as seeds for the rapid growth of supermassive black holes. These seeds would have had a significant head start, existing long before the first stars and galaxies formed. As matter began to clump together under the influence of gravity, PBHs could have accreted surrounding material, growing larger over time. This process, combined with mergers between primordial black holes and other black holes, could explain how today's supermassive black holes reach such enormous sizes in a relatively short period. To understand this better, imagine planting a tree. If you start with a sapling, it will take many years to grow into a towering oak. But if you start with a larger tree, its growth to maturity will take far less time. Similarly, PBHs would act as larger seedlings compared to black holes formed from the collapse of stars, allowing them to grow into supermassive black holes much faster. The potential role of PBHs in galaxy evolution extends beyond their function as seeds for supermassive black holes. PBHs could have influenced the distribution of matter in the early universe, shaping the formation of galaxies and galaxy clusters. Their gravitational effects, even at small scales, could have contributed to the clumping of matter, creating the first gravitational wells that attracted gas and dust to form stars and galaxies. In addition, the radiation and energetic particles emitted by accreting primordial black holes could have affected the surrounding environment, heating nearby gas and influencing the rate of star formation. This feedback mechanism may have played a role in determining the structure and dynamics of early galaxies. Furthermore, these enigmatic objects could provide clues about the nature of dark matter. If they account for a significant fraction of dark matter, their distribution and behavior would directly impact the formation and evolution of cosmic structures. By studying the effects of PBHs on the large-scale structure of the universe, scientists can gain insights into both dark matter and the conditions of the early cosmos. While the idea of primordial black holes is intriguing, proving their existence presents significant challenges. PBHs are difficult to detect directly because they do not emit light or other electromagnetic radiation. Instead, scientists must rely on indirect evidence, such as their gravitational effects on surrounding matter or their potential contribution to gravitational wave signals. Upcoming experiments and observatories offer new hope for uncovering the secrets of these objects. Projects like LISA, the Square Kilometre Array, or SKA for short, and future gravitational wave detectors will provide more sensitive tools for studying black holes and their interactions. These instruments could help identify signatures of PBH mergers or detect their influence on cosmic structures. In addition, theoretical work continues to refine our understanding of PBH formation and their potential role in the universe. By simulating the conditions of the early universe and comparing these models with observational data, scientists can test the plausibility of PBH scenarios and explore their implications for cosmology. The formation of primordial black holes is a fascinating chapter in the story of the universe. These ancient objects, thought to be born in the first second of cosmic history, could hold the key to some of the greatest mysteries in astrophysics, from the nature of dark matter to the rapid growth of supermassive black holes. While much remains unknown, the pursuit of answers about PBHs is a testament to the ingenuity and curiosity of human science. By studying these elusive objects, we not only learn about the universe's past, but also gain a deeper appreciation for the intricate and interconnected processes that shaped its evolution. The universe we inhabit is a place of remarkable precision. From the speed of light to the strength of gravity, the fundamental constants of nature are fine-tuned to values that allow for the formation of stars, planets, and ultimately life. These constants, which govern the very fabric of reality, raise interesting questions about the nature of existence. Are these values the result of chance, a grand design, or the influence of a multiverse? In this chapter, we'll explore the mystery of these constants, their implications for the universe, and the profound role they play in shaping our cosmic story. Fundamental constants are the bedrock upon which the laws of physics are built. These unchanging numbers determine how forces interact, how particles behave, and how the universe evolves. Some of the most critical constants include the speed of light, also known as c. At approximately 299,792 kilometers per second, the speed of light is a universal limit that governs how fast information and energy can travel. The Planck constant, or h for short. This tiny number, 6.626 times 10 to the negative 34 joule-seconds, sets the scale for quantum mechanics, determining the behavior of particles at the smallest scales. The gravitational constant, or capital G. This measures the strength of gravity, determining how massive objects like stars and planets attract one another. The fine structure constant, or as scientists call it, alpha. It is a dimensionless constant that characterizes the strength of electromagnetic interactions. What makes these constants so extraordinary is not just their existence, but their precise values. If any one of these constants were even slightly different, the universe as we know it would be unrecognizable. For example, a slightly stronger gravitational constant might have caused the universe to collapse in on itself shortly after the Big Bang. A slightly weaker gravitational constant might have prevented the formation of stars and galaxies altogether. Variations in the fine structure constant could alter the chemistry of the universe, preventing the formation of complex molecules essential for life. These constants are like the dials on a control panel, each set to an exact value that allows the universe to function. The odds of all these values aligning in a way that permits a habitable universe seem astronomically low, prompting scientists and philosophers to ponder the significance of this fine-tuning. The fine-tuning of the universe raises many questions about its origins and purpose. Broadly speaking, there are three main interpretations of this phenomenon: coincidence, divine tuning, and the multiverse hypothesis. Let's start with the first possible interpretation, according to which the fine-tuning of the universe is simply a coincidence. This perspective suggests that the constants of nature are what they are by chance, and we just happen to live in a universe where the conditions are right for life. While this explanation requires no assumptions beyond randomness, it leaves many feeling unsatisfied. The improbability of such precise values emerging by chance, when even slight deviations would render the universe lifeless, strains credulity for many. Imagine rolling a die with 1 trillion sides and landing on exactly the right number to create a habitable universe. While not impossible, it's a scenario that seems almost too improbable to accept without further explanation. Another interpretation is that the universe's fine-tuning is the result of intentional design. In this view, the precise values of the constants reflect the work of a creator or higher intelligence that set the parameters of the universe to allow for life. This perspective is often rooted in theological or philosophical traditions, which see the order and harmony of the universe as evidence of purpose. Proponents of this idea argue that the fine-tuning of the constants is akin to finding a watch on a beach. The intricate design and functionality of the watch imply the existence of a watchmaker. Similarly, the fine-tuning of the universe could imply the existence of a cosmic designer. However, critics of this view argue that invoking a designer raises further questions. Who or what designed the designer? And why were the constants chosen in this particular way? The third interpretation is the multiverse hypothesis. This approach suggests that our universe is just one of many. According to this idea, there could be a vast or even infinite number of universes, each with its own set of physical constants. In most of these universes, the conditions would be inhospitable to life. However, in a small fraction, including ours, the constants align in a way that allows for stars, planets, and living organisms to exist. The multiverse hypothesis provides a naturalistic explanation for fine-tuning. If there are countless universes, the existence of at least one habitable universe becomes far more likely. To take it one step further, if there are an infinite number of universes, there has to be an infinite number of habitable universes too. However, this idea comes with its own challenges. For one, the multiverse is inherently difficult, or probably impossible, to test or observe, leading some to question whether it qualifies as a scientific theory. Additionally, the multiverse hypothesis raises philosophical questions about whether we can ever truly understand the nature of reality if we are confined to observing just one universe. The precise values of the fundamental constants are not just academic curiosities, they are directly responsible for the existence of stars, planets, and life itself. To understand their importance, let's examine a few key processes that depend on fine-tuning. Let's start with star formation. The balance between gravity and nuclear fusion is essential for the formation and stability of stars. If gravity were slightly stronger, stars would burn through their fuel too quickly to support the development of life. If gravity were weaker, stars might not ignite at all. Now, let's take chemical complexity as another example. The fine structure constant governs the strength of electromagnetic interactions, which in turn determine how atoms combine to form molecules. If this constant were slightly different, the universe might lack the chemical diversity needed to support life. Last but not least, nuclear reactions. The strong nuclear force holds atomic nuclei together, while the weak nuclear force governs processes like radioactive decay. The precise balance between these forces is essential for the production of elements like carbon and oxygen in stars, which are crucial for life as we know it. Fine-tuning also extends to large-scale structures like galaxies and planetary systems. The distribution of matter in the universe, the stability of planetary orbits, and the conditions for liquid water all depend on the interplay of finely tuned constants. Without this delicate balance, the emergence of life would be impossible. The fine-tuning of the universe has inspired both scientific inquiry and philosophical reflection. For scientists, the challenge lies in understanding why the constants have their particular values and whether they could have been different. Efforts to unify the forces of nature through theories like string theory or loop quantum gravity may eventually provide insights into the origins of these constants. Philosophers, on the other hand, grapple with the implications of fine-tuning for our understanding of existence. The question of why the universe is structured in a way that allows for life touches on profound issues of purpose, meaning, and causality. Are we the beneficiaries of a fortunate accident, the creations of a purposeful designer, or the inhabitants of one universe among countless others? These questions challenge us to think deeply about the nature of reality and our place within it. The fine-tuning of the universe's constants is a mystery that lies at the intersection of science and philosophy. While we may never fully resolve the question of why these constants have their specific values, the search for answers continues to inspire new discoveries and insights. By studying the laws of physics and the structure of the cosmos, we not only uncover the mechanisms that govern the universe, but also deepen our appreciation for its complexity and beauty. Whether the result of chance, design, or the multiverse, the fine-tuning of the universe remains one of the most awe-inspiring aspects of existence. It reminds us that even the smallest details can have profound consequences, shaping the cosmos in ways that make life possible. As we continue to explore this mystery, we come closer to understanding the fundamental nature of reality and the extraordinary conditions that allowed us to exist. The universe, with all its grandeur and complexity, continues to pose some of the most profound questions ever asked. From its explosive beginning in the Big Bang to the intricate dance of particles and forces that shaped its structure, the story of the cosmos is a journey through mystery, discovery, and awe-inspiring wonder. And yet, even after centuries of scientific progress, the ultimate question remains: how did it all begin? The origin of the universe, as far as we can understand it, is a narrative still being written. Theories like inflation and quantum gravity have provided incredible insights into the cosmos's first moments. Alan Guth's theory of inflation explains how the universe expanded exponentially in its infancy, solving puzzles like the horizon and flatness problems. Quantum gravity, though still incomplete, aims to reconcile the small-scale world of particles with the large-scale fabric of space-time, promising a deeper understanding of phenomena like the Planck era. And yet, these theories leave us with open questions. What exactly triggered inflation and why did it end? How do gravity and quantum mechanics merge into a single unified framework? What role do exotic entities like right-handed neutrinos or primordial black holes play in shaping the cosmos? These gaps in our knowledge remind us that the universe still holds secrets waiting to be uncovered. The journey to understand the universe's origins is far from over. In fact, we stand on the brink of discoveries that could transform our understanding of these early moments. Relic neutrinos, for instance, represent a direct link to the universe's earliest moments. Escaping just 1 second after the Big Bang, these ghostly particles carry a snapshot of the conditions that existed during that brief window of time. Detecting and studying relic neutrinos would provide an unprecedented look into the universe's infancy, helping to refine or even rewrite our theories. Primordial black holes, another tantalizing possibility, could offer clues about the density fluctuations that existed during the universe's first second. If they exist, these ancient objects could explain the rapid formation of supermassive black holes and perhaps even account for a portion of dark matter. Detecting their gravitational effects or signatures in gravitational wave data could shed light on some of the most perplexing mysteries in astrophysics. Moreover, advances in technology and observational techniques promise to push the boundaries of what we can detect and measure. Next-generation telescopes, particle accelerators, and gravitational wave observatories will allow us to probe deeper into the fabric of reality. Maybe one day we'll be able to test theories like string theory, loop quantum gravity, and the multiverse hypothesis. Each new discovery will bring us closer to understanding the first moments of time and the mechanisms that gave rise to everything we see today. Understanding the universe's origins is not just a scientific endeavor, it is a deeply human pursuit. The cosmos is, in a sense, a reflection of ourselves. Every atom in our bodies was forged in the heart of a star, and the forces that shaped galaxies are the same forces that govern our daily lives. By studying the universe, we are not only exploring the external world, but also connecting with the fundamental principles that define our existence. This connection is both humbling and inspiring. It reminds us that we are part of a much larger story, a story that began 13.8 billion years ago with a burst of energy and continues to unfold in the galaxies, stars, and planets that populate the cosmos. Each new discovery adds a chapter to this story, deepening our understanding of who we are and where we come from. The mystery of the universe's origin is unlikely to be solved overnight. It may take decades, centuries, or even millennia to answer some of the most profound questions. But the pursuit of these answers is, in itself, a testament to the power of human curiosity and ingenuity. Science thrives on questions, and the universe provides an endless supply. Each new theory, experiment, and observation brings us closer to the truth while simultaneously revealing new layers of complexity. It is this dynamic process, the interplay between the known and the unknown, that drives the progress of science and keeps the quest for understanding alive. As we look to the future, the possibilities are as vast as the cosmos itself. From relic neutrinos to primordial black holes, from quantum gravity to the multiverse, the next chapters in the story of the universe promise to be as exciting as the ones that have come before. The answers we seek may not only change our understanding of the cosmos, but also reshape our perspective on existence, purpose, and the nature of reality. Thank you for joining me in this journey. If you like the video, don't forget to like it and subscribe to the channel for more videos like this. Thank you.